Alright, so we are moving on to chapter 4.2 about traveling waves. So you may ask me, shouldn't all the waves be traveling, propagating energy? And the answer is not really. There is something called standing wave. If you scroll down all the way to 4.5, it's called standing wave. So traveling wave is something that you have learned in probably IGCSE and maybe junior science, and standing wave is something new that I think you may not have learned before. I don't want to go deep now, but just to show you an idea how standing wave would look like. So in this video, you can try to see a demonstration with a slinky here and trying to make a certain frequency. As you can see, there are points where like the N, which is called the note which we will learn in the future, represent the point where it doesn't really have any amplitude. While for the other parts, they may have certain amplitude, but then the amplitude is not even uniform. And so in this case, it's like the wave standing, right? Or we can also call it stationary wave. Anyway, let's come back to traveling wave. And in fact, if you have studied IGCSE physics before, the whole subchapter of 4.2 should just be very easy for you because you have learned all of these already. So for now, I would like to give you some time. You can go and try to recall your memory about all the terms here. So these are the expectations that IB Physics would like you to have in this subchapter. So pause the video and try to recall your memory about all these concepts.
A few moments later.
Alright, so now I'll quickly do a recap for you in case you don't recall all these things, and I'll tell you the key ideas that you need to understand. So first of all, the idea of traveling waves. In fact, for wave, you can find the definition from the textbook, which you can see here. A wave is a disturbance. This is a very important word. Disturbance means the particles will be moving around that travel in a medium. It can be vacuum for electromagnetic wave. So for other wave like the sound wave, which I'm talking, or the slinky itself, or it could be the water wave, they are all mechanical waves. So that would require a medium to transfer the energy. So those medium will be referring to the particles that are actually vibrating. However, for electromagnetic wave, it's a very special wave that they don't actually require any particle. Alright, and they would transfer the energy and momentum from one place to another, and the direction of propagation of the wave is the direction of energy transfer, and there is no large-scale motion of the medium itself as the wave passes through it. So for the last sentence, what it means is, for example, if you try to swing the slinky, the whole slinky itself is still staying there. Or if you think about when you swim, you're kind of making the water wave. And so the sea or the swimming pool is still there always. The whole swimming pool or the whole sea itself. You won't be having the sea moving around, on the earth. So even though the wave is moving forward, but the medium itself doesn't really have a movement. Alright, next I want to talk about the transverse and longitudinal wave first. So this is a very good animation that I find, and you can see this is a longitudinal wave, which for a slinky, you kind of like holding it and then push it forward. And this is how you can produce a sound wave as well. If you try to observe those loudspeakers and looking at the diaphragm, this is how they do as well. And so sound wave itself is a longitudinal wave, of course, and you can see right here, this is like a diaphragm. So you're trying to push it away, and so that particular layer of air will be compressed and sending forward. And you can also see the vibration of the air particle itself. For example, the red dot here, it doesn't really move forward. So that coincides with what we said earlier. The medium itself doesn't really travel through in a net movement. They are vibrating along a certain equilibrium position. But if you try to look at the compression, is moving forward as a whole, like the Mexican wave, if you have seen in those kind of ball match or competition before, or sports day. And then the next thing that you want to see is the movement direction of the particle. In this diagram is going from left to right, so horizontally. And also the wave propagation is also going horizontally. So for longitudinal wave, the fundamental definition versus the transverse wave is these two directions. So I'll say again, the direction of the particle movement and the direction of the energy propagation, or the wave traveling direction. they are parallel. Okay, so this is definition of longitudinal wave. While for transverse wave, you can see that the particles are moving up and down in this diagram, while the wave itself, when we try to look at the whole, it will be going horizontally. So they will have a 90-degree, and therefore we said it is perpendicular in terms of direction for the displacement of the particle and the direction of wave propagation. So this is the fundamental classification criteria for transverse wave and longitudinal wave. Next, it will be about the wavelength, frequency, period, and wave speed. So let's talk about wavelength first. No matter what wave you are talking about, there must be wavelength, and also that will be related to frequency, as you may know. So for the diagram here, longitudinal wave, you can see if I try to freeze and try to take a screen capture, for example, then the wavelength will simply be the distance from a certain compression. So I can draw a line. This is a compression, this is another line of compression. So between the same phase, if you recall what you learned in 4.1, we talk about the idea of phase. So for the 2 points which have the same phase and which they are the closest one, then this is one cycle, right? And the distance between them is one wavelength. Of course, you can point out from another point, not necessarily compression, it could be the rarefaction. So it could be, I know this is compression, this is compression, so somewhere along here should be the rarefaction, and somewhere along here should be another rarefaction, and this should also be the wavelength as well. Similarly, for transverse wave, I can also take a screen capture and then try to analyze it, and here we can have the peak, or we call crest, to another crest, and that will be again one cycle, and this should be one wavelength. So similarly, I can pick another point. Again, it doesn't really matter which point you take as long as it is one completed cycle. So I can take, for example, this point as in the trough, and here that will be also the wavelength too. Next, frequency and period. So if you recall the definition of frequency, it is how many cycles per second. The unit is hertz, or you can also call it how many per second. So S -1 if you want to say. And for period, the symbol is T and the unit is S, and that is how much time it takes for one cycle. So that's the unit. And if you try to build a relationship between them, or state relationship between them, that is F equals to 1 over T, or the other way around, T equals to 1 over F. And so if you want to measure the frequency of a certain source, I think it will be much easier to measure its period first. So let's try to do it now. Let's take the animation here as an example, and I will try to measure 5 cycles and how much time it takes. So I'll start the time when this bar, which is supposed to be the one making the wave, when it's on the most left. Okay, so let's try. Go. 1, 2, 3, 4, 5. Okay, so it's about 12.82. So if you come back here and try to do a bit of calculation, 12.82 seconds is going to be 5 cycles. So divided by 5, then you'll be able to get the actual period T, which is about 2.564 seconds. If you use the relationship, this is just a mathematical relationship that we have, because I mean, just by the definition, if frequency is how many cycles per second, and T is how many seconds it takes for one cycle, then that's naturally the consequence of the mathematical relationship that they have. So eventually you can calculate by 1 divide the answer that you have. So that means the frequency is actually 0.39 hertz. Okay, for the animation that we have just now. So it means for 1 second, it doesn't even have one wave. It just have about 0.39 of the cycle of the wave itself. Next, the wave speed. Fundamentally, if you try to think about a wave and the idea of the speed, then you know that speed or velocity v equals to, by definition, distance over time or displacement over time. So if you think about the wave, just grab a certain point and then you just wait until maybe it keep moving to another certain point, and somehow let's say you know it took 10 seconds to move say 5 meters, then technically you can always calculate using this equation and find out the speed of the wave. But then usually you don't have such a way. Instead, you probably would be able to find out the frequency and also the wavelength, and therefore there's an equation called v equals to f lambda that you have learned in IGCSE. However, I wonder how many of you truly derived this equation before. So right now, I think it's a good chance for you. Please pause the video and try to think about how we can derive this equation. So pause the video now.
A few moments later.
Alright, so here's the answer. If you consider a wave, alright, again, doesn't really matter what wave it is, but then if you recall, we talk about the definition of the wavelength 1 lambda, and also we talk about the definition of period t. So period is how much time it takes for one cycle to be produced, and lambda is how much length for one cycle, that means one wave, to be produced. And therefore, if you just by using the idea definition of v equals to distance over time, and if you put it into the context of only one complete cycle, then that's basically what you have. Lambda divided by the big T, period. And so in fact you could have an equation called v equals to lambda over t, and because t in itself equals to 1 over f, the relationship between period and frequency, and therefore you have the equation v equals to f lambda. This is how you derive this equation. Amazing. Next, electromagnetic waves. So just now we already mentioned EM wave is one of the only waves that can travel through the vacuum, and that's because the wave itself looks like this. Yes, it consists of electric field and magnetic field. That's why it's called EM wave. And if you try to look at the vibration of the field, you can see they are always 90 degrees to each other, and that's something to do with the hand rule that you have learned in IGCSE or in chapter 5 earlier. The other thing that you may want to pay attention to in up to this chapter, chapter 4, IB Physics, is the EM wave spectrum, which again you may have learned it in IGCSE already, and it starts from radio, microwave, all the way until gamma ray. There was a very interesting song about the electromagnetic wave and help you to memorize it, so I'll recommend you to revisit that again. However, there's something more about EM spectrum in IB Physics is, if you look at here, this is a disaster to me because it expects you to remember. Alright, they say aware, but it seems like they want you to remember the order of magnitude of these EM waves. So let's just have a quick look. So here we have the visible light in the middle, of course, but then the radio wave actually has a wavelength of a few hundred, so 300, okay, and or up to a certain integer, I mean not integer, but 1 digit meter, so like 3 meters. And while for a few centimeter would be like microwave, while for infrared all the way, I think I wouldn't be able to remember this as well, but then I would know that gamma ray is extremely small, and that is like 10 to the power of negative 14, or like to an order of magnitude of close to be a nucleus roughly. So if you recall the size of a nucleus, and that would be somewhat between 10 to the power of negative 15. Other than that, the visible light is certainly something you should remember for sure. That's the red light is 700 nanometer, and the violet light is about 400 nanometer. So later on when we learn the other chapter in 4.3 and 4.4, there are always some question about the different color of light, and you need to do some calculation with that. And this will be the number that you kind of see quite often. Next, the nature of sound wave. So I think we just mentioned that sound wave is a longitudinal wave, and it required the particle to vibrate to transfer the energy. And so this is the basic idea of sound waves. Of course, for all the waves, they will have the phenomena or property of having reflection, rarefaction, and diffraction and interference, which we'll talk about in the next subchapter. Next, application. So explaining the motion of particles of a medium when a wave passes through it for both transverse and longitudinal cases. I think this is basically what we mentioned. So like for the wave that we have, like here, no matter longitudinal or transverse here are moving from the left to the right, but then the particle vibration is different directions. So for longitudinal is parallel to the wave propagation direction, transverse will be perpendicular. And the next thing will be a bit new to you probably. It asks you to sketch and interpret the displacement distance graph and displacement time graph for both waves. You probably have seen displacement time graph a lot in mechanics, and you may be wondering, hey, so what is displacement distance graph? Like, how does it even make sense to have two dimensions to put on the same graph? And here is the answer. So for example, you have the y-axis to be the displacement, which is talking about a particle, how far does it displace from the equilibrium 0 over here. And horizontally, the x-axis is the distance, which is talking about along the whole slinky, for example, or along the axis that you're observing, then that will be the distance. So basically, it's exactly the shape of the wave that you have, okay, over here. However, one thing you should notice is showing you this graph is not necessarily showing you the transverse wave. You may also have a longitudinal wave as well. So for example, for a compression and a rarefaction, it could be these two extremes. So because when the particle move away from the equilibrium the most, it should be the compression and also the rarefaction itself. So it will be these 2 points. So the shape is exactly the same. So having this graph will not be able to tell you whether it is transverse or longitudinal. More importantly, you'll be able to observe, for example, for one particular particle. So here, this is an exceptionally good diagram to show you at this point. I think this is like 27 cm, so it's just a random particle at a particular point. If you try to look at over time, from 0 millisecond all the way till 3 milliseconds, look at just this black dot, all right, at the highest point going down even further, and this is like the bottom that it reached, and go back up again and go back up again over the equilibrium point and go back to the highest point. So this is like one cycle from the highest point going to the bottom and go back to the highest point. So if you try to convert, I don't know whether they provide you a graph. I think this one, no, sorry, this is not, or I don't know why they don't provide you. If you try to draw a diagram of these particles, so you'll be able to produce the one that they say, displacement time graph. So I think the diagram should look like this. If I try to draw a map from this displacement distance graph to a graph that only describes these particular particles. So at the beginning, it is at 1. You can see the y-axis has no like specific unit, so it's an arbitrary unit, so I'll just put it as unit here. We will start at 1. Okay, so this is a starting point, and then after half second it will be about 0.25, so around here after 0.5 second, and then 1 second it will be like negative 0.75, so roughly here. Sorry, I didn't have a good scale, and so around here for 1.0. So similarly, you can have next one to be 1.5 is reaching the bottom, so around here for -1, and then you can also map again back to negative 0.5 when it is at 2.0 millisecond, so around here. 2.5 when it is almost reaching back to the top, and then 0.0 millisecond is the one that we know. So if you try to connect all this line, then you'll be able to obtain a sine wave also. Well, not necessarily sine wave, it could be cosine, but you know what I mean, yeah? The curve itself. So in itself, it also look like the wave itself. And in fact, the reason why we have 4.1 simple harmonic motion put earlier than 4.2 talking about the basic idea of wave is because this particular particle, and in fact all the particle along the whole wave, each of them is performing a simple harmonic motion, and they may just have a different phase. So for the peak to another peak, these two particles, so like the Q here and another particle, I don't know what it's called, P or whatsoever, these two, they will be having in phase if you consider they are both performing the simple harmonic motion.
Explosion.
Alright, so that's pretty much it, and in the next video we're trying to do some basic problem solving involving the wave speed, frequency, and wavelength. So basically using the idea of the equation here. And for the experiment finding out the speed of sound, we'll also talk about it in a later part of the video. Okay, so I think that's all for the quick recap of the basic concept of wave that you have learned in the past years. I'll see you again in the next video. Bye!